And welcome to another video. Today we're going to be doing 958 check completeness of a binary tree. So given the root of a binary tree, we want to determine if it's a complete binary tree. And in a complete binary tree, for every single level except the last one, you want for every single level except the last to be completely filled and all nodes in the last level to be as far left as possible. You can have between 1 and 2 to the power of h nodes inclusive at the last level h. Okay, if this makes sense, we can take a look at the example over here, and we'll see that for 1, 2, 3, 4, 5, 6, the output's going to be true because every level before the last is full. For this one, you want to return false because the node with level 7 isn't as far left as possible. Okay, that makes sense. Just an initial thought between this, we can either do like a DFS or a BFS, but I think a BFS would be better because the nature of this question forces you to go for every single specific level before we move on. So I think we can do a BFS, and then we can do a BFS that checks to see whether or not a certain like if you ever encounter a null value, if you ever encounter a null value, you have to know that every single node past that value is going to be null, otherwise it's going to be a false, because it says here all nodes in the last level as far left as possible. Like let's say like we have like the 3 and the 3 doesn't exist over here, right? If the 3 doesn't exist over here, then you'll know that every single element after in the tree will have to be null. So like every single thing that's added. But because the BFS adds the 4 and the 5 first, we'll know that's not true, so it's going to register as false, right? And likewise, if everything is going to be true, like if it's just like its original one, and you keep popping and all of them are going to be null, there's nothing left in the queue, then we know it's going to be true. So I think just by checking to see whether or not there's anything in the queue left that is a null, that is like non-null, we can like effectively figure out whether or not something of the binary tree is complete. So if that makes sense, I'll go ahead and begin coding it up now. What we're gonna do is we're gonna have first of all we're gonna have a queue, and that's gonna be just like a deck of just the root value starting initially. And then what we're gonna do is we're gonna go while queue. We're gonna want to check to see what the cur is. So we want to do cur dot pop equals q dot pop left. And then from here, what we want to do is if the cur exists, then what we're going to want to do is just add the children as normal. So we want to do cur dot appends, or like we want to do a q dot appends cur dot left, q dot appends cur dot right. And then otherwise, if that element doesn't exist, then the first thing what we want to do now, if it doesn't exist, is we want to check to see for every single element in the queue, while queue, you want to check to see if cur dot pop left is a valid value, then you want to return false, because that means it's not a complete binary tree like we were saying from before. Now if it is a binary tree, like a complete binary tree, then we can go ahead and return true. So we have return true over here. So just to walk us through a couple of cases, what we can do is we can have a check to see. First, we add the 1 here, and then for every single level, we'll go ahead and check, right? So for the queue, one just got added. Then that adds the children to the left and the right. 2 and 3 get added because it exists. So now it's going to be looking like this. I'll have like a 1, this gets erased, 2 and 3 gets added, and then this one happens, and then we pop it from the left again. 4 and then 5 get added, and then 3 and then 6 gets added, right? And then at the very end, you'll notice that like there's going to be no nodes left, so it's going to end up returning the final value. It's going to return true while the queue exists. If the current exists one, then you're gonna add that, and you want to do this if the so you want to do it for 4, 5, and 6, and it'll eventually return because it'll never encounter a null node for every single one. Yeah, and then for this example here, it's gonna add 1, then it's gonna add 1, then it's gonna go ahead and pop that. It's gonna add 2 and 3, and then after that it's gonna add 4, 5, and 3. And it's gonna pop this, and then it's gonna check to see for the elements if they're non-null nodes, which they are, like those values are valid, then it's going to return false. So if you go ahead and run this value now, Okay, so while cur is equal to q.pop left, actually, we have to keep popping it from here. So from here, if the current exists, then that's actually when we're going to do it. So if the current exists after you pop it, then you want to return false. Otherwise, you want to return true because it's going to be an empty one. So if you go ahead and run this now, it's accepted, fully good. The time and complexity of this one is going to be O of n, because in the worst case, if you have a strange tree, in the worst case scenario, you're going to be having everything added to the queue, like a sparse tree. And in the space complexity of this one is going to be O of n as well, because in the worst case, you could be storing everything here. Yeah. Well, actually, yeah. And time complexity is going to be O of n, and space complexity is going to be O of n as well, because in the worst case, you might encounter something like a sparse tree, which is going to add every single element into the queue. So yeah, that's it. Thanks guys for watching.